With that, I'm going to stop sharing my screen and hand over to our first speaker of the day. So unless there's any questions or comments, over to you, Bruno.
Thank you very much indeed. I will share my screen. I have quite a few slides and only 10 minutes. Thank you for the space, IoT London, for telling my story. I hope some of it might be useful to people and their questions might indicate that. There is an air quality monitoring puzzle, and clearly it's going to be solved through IoT in some form or another. And let's step through it. I should say, first of all, that I'm a co-founder of a company, a little company called Sadco Science, founded in 2016, whose founding investor was a UK company called AlphaSense, who make sensor components. And we began life kind of like their backroom boys to do, their backroom people to do electronic design and software, and then got greedy and said, we want to make devices that do air quality monitoring, because that's what the money is, surely. And this is the goal. So here we have a heat map of pollution density in the West End of London. I believe this heat map comes from King's College or its associates, and is based on a mixture of readings, actual readings by real air quality monitoring devices. The vast majority of these squares are, of course, not real readings at all. They're estimates according to quite sophisticated models. They tell you this map tells you one thing that I think is generally true in urban areas, which is that pollution, the stuff that kills you, varies enormously over short distances. You go one block away and your exposure to lethal pollution changes. But actually by how much? How is this model validated? Well, it's not. It's just a lick your finger and stick it in the wind type thing to a large extent. Some streets may be used as rat runs by motorists. This model can't really accommodate that. And in the end, what we want to do is to monitor as many places as we possibly can, maybe down to the level of personal exposure, one monitoring device per person, but at least at the block level. And then what technology could you use to do that? Well, here's a choice. On the left is a stack of gas concentration monitoring devices, each one focusing on a specific gas. The top one is carbon monoxide. And they use a chemiluminescence process, which is a very stable, very accurate way of measuring, very reliable way of measuring toxic gas concentrations. Unfortunately, a stack like this, together with the little air-conditioned booth that it sits in, will cost you about £50,000 and take up the space of maybe 2 telephone booths. So you're limited in where you can put these things. This really, really cute device on the right is a personal exposure device. You could strap it to your belt buckle, your belt, and it would measure particulates and perhaps one gas, maybe nitrogen dioxide, a particularly nasty gas. It's particularly common amongst urban traffic, but it's not very accurate. Really, it's little more than a random number generator. And you can go on the website of the company that would sell you this for $129, which is certainly a bargain compared to £50,000. And they will show you how accurate their device is. The bit that they put in small print is that their tests were done in a laboratory under very controlled conditions. And what the people in this business all know is that doing it in the field is what counts. And measuring in the field in quickly changing conditions of temperature, humidity, wind speed, and so on, kind of screws up for lab results. About 2017, South Science began a conversation with the United Nations Environment Programme, whose headquarters in Nairobi, to design a device that could measure pollutant gas concentrations and particulates that was very robust. It would work in a very wide range of environmental conditions, from very cold to very hot to very wet to very dry, that could survive rolling blackouts of mains power and frequent, often long-running disruption to internet connections, whether they were via cellular networks or Ethernet networks or whatever. And this is the inside of what became the South Science Practice Urban product, which is still available, which has certain features. It uses a BeagleBone off-the-shelf processor card because the United Nations like the idea of open source hardware. And almost all of the software that runs on it is open source, including the Debian operating system and our Python code that runs on top of it. And that gave us a way of understanding how IoT devices work in the real world. I should just add that based on the experience of that, we developed our own custom processor card, which is again a low power Linux class processor with modem and various sensor interfaces that just makes the device more robust, cheaper to make, and so on. We manufacture both in parallel. They're used for slightly different settings. And of course, it's not just, IoT isn't just hardware, it isn't just electronics. And enabling technology for a company like South Science is the data infrastructure. We didn't begin with Amazon Web Services, but we moved there, I think, at the right time, when their kind of leading edge had become a leading edge in terms of MQTT messaging and various data storage and so on technologies. So we run a very big data store for hundreds and hundreds of devices, all reporting in real time every couple of seconds or so, all across the world. So we have some single points of failure in this system that so far haven't failed. Since we stabilized what we did several years ago, we've had 100% availability of this system, 100%. That doesn't mean all our devices always work all the time, but the cloud system does. So here is a picture I took on the top of a school in Addis Ababa in Ethiopia. The guy on top of the ladder with one of our devices is one of the United Nations Environment Programme bosses who loves any excuse to get away from an air-conditioned office and go up a ladder. And we were doing a co-location study here with reference particulate equipment. Particulate pollution is an enormous problem in Addis Ababa and pretty much any other city in the developed world I've visited. And it was in settings like this that we learned how hard doing real world data for pollution monitoring is. Because we could run in all these places, we collected lots of interesting data. The upper chart here is marked sulfur dioxide. Looks like it kind of maps the relative humidity blue chart below it. And it does. Of course, not quite. But you sort of screw up your eyes, which is a great thing to do when you're looking at timeline charts, and try and understand what the relationship between these various extraneous factors like temperature and humidity on a gas electrochemical sensor like the sulfur dioxide sensor is. So the sulfur dioxide signal is wrong, right? Within it, though, is a correct signal. Something that tells you what the actual sulfur dioxide measurement is, not what the sensor is telling you. So we had a complicated problem in front of us, but we knew we could solve it for two reasons. And the first one we call accuracy. Here is a gas electrochemical sensor running in a laboratory under very controlled conditions, and its linearity against known concentrations of, in this case, nitrogen dioxide is very, very accurate. It's good. It's totally repeatable as long as you get conditions right. And here's another chart where we put, in this case, two NO2 sensors beside each other in the field. And most of the time they're wrong. But the fascinating thing was they're always wrong by the same amount. So those two aspects, the behavior of these sensors, is complex, but provides a foundation to do something interesting. We tried to solve this problem using what I crudely call physics. In other words, come up with an idea on a whiteboard of what you think, how you think the sensor will behave based on what you know about the chemistry and the materials in the device. But we found we had too many terms to deal with. So we turned to machine learning. And it was natural to do this in the AWS world. And we got good at it. We found that we could kind of manufacture machine learning models. In other words, we were applying the same rigor that we applied to production software to creating machine learning models so that we could control our experiments and understand our experiments and catalog them. And at the last live AWS event at Excel in London, a couple of years ago or so now, I had a wonderful one-to-one with a AWS machine learning architect. And she said to me two really important things. One of which is, you don't need huge volumes of data, you just need data quality. And the second one she said was, the key term will be something you didn't think of. And she was absolutely right on the two things. And we run co-location experiments around the world now, where we collect data with our devices alongside the big expensive reference equipment and collect data in environments, different environments. And we build quality data sets out of that. And this is one of the sulfur dioxide. The sort of results you get from that, this was an early nitrogen dioxide experiment. And you can see the sort of jump in organization of the machine learning model output was shepherded these data points together in quite a satisfying way. But how good is good? This is some work we did with optical particle counters that use a little laser beam inside a black box, and they measure how the light is scattered and try to estimate the particle sizes are in the particulate pollution that's drawn through the box. And we reached the point where we passed the MCERT's formal standard for data quality. We're currently involved in an audit to complete that work in terms of manufacturing, but it's going to go through, that said, yes, now we have taken a small, low-cost sensor component, and through the design of the sensor device, but this machine learning process created something that's comparable to the reference equipment. And the cute thing that we've done with AWS is to say, well, once you've got that, you can compile that model and you can deploy it to a device. So every device we ship has those models running on them. Do you need to do that on the device? Could you just do it in the cloud? Well, we have certain principles, like we say, every sense reading, and devices tend to read every 10 seconds throughout their lifetime, is stored on an SD card on the device. So, you know, a 16 gig or 32 gig SD card will store the entire lifetime's exposure to the environment of the device. And that should include all the data interpretation. You shouldn't have to go to the cloud. And anyway, there are people who use our devices traveling around on the London Underground where they have no hope of a network connection, and they still need to record the data on their devices. So we can build machine learning models in the cloud, catalog them, and deploy them to devices. And there's lots of other reasons why you might want to do something on the device, back the latency of the result and so on. And the devices create records every few seconds that kind of look like this. So it says this has interpreted it says exeg value for NO2 of 12 parts per billion. And we just keep going. This is my final slide, and it's a location just northwest of Pretoria in South Africa, and it's a platinum mine and smelting works that has extraordinary levels of both NO2 and mainly sulfur dioxide. We're about to release the machine learning model that we got from that. And what you see on the top line here is a pale gray line and a brown line. And the brown line is the output of the machine learning model, and the gray line is the output of the sensor itself, the input to the machine learning model. And you can see that the relative humidity, the blue line below, is having a really complicated relationship with the sensor, but the machine learning model has cleaned that up and given us actually a meaningful chart. So we're feeling kind of good about these things, and can maybe share some stories in this long and sometimes painful process of doing edge machine learning.